So actually, the agenda of I will give just a very brief introduction just to recall what is the problem and what kind of limitations we aim to solve. And then I will explain the conceptual relevance index in a bit more detail. And after that, I will highlight some of the results. And eventually, I will end up with the conclusion. So in the first place, so why is the detection of relevant concept an interesting and important challenge in FCA, especially with the advent of big data era? So actually, as we all know, in FCA framework, we usually use the concept lattice as a model to represent and extract knowledge from the context of the problem. Normally, the context of the problem contains exponential number of formal concepts, but a formidable number of these concepts contain irrelevant and redundant information. So the problem is these irrelevant concepts frequently induce a high computational complexity even with the small applications, and most of the time results in generating a redundant and irrelevant association rules. So that's why it's important to prune all the irrelevant concepts from the lattice before generating the implications and the association rules later on. So actually, there are many traditional strategies that can be applied to mine the interesting pattern in the lattice, but in our we focused on the concept selection strategy. So in this strategy, we select the relevant concept after evaluating its quality using an interestingness measure. So there are several interestingness measures actually have been introduced in the FCA literature. For instance, the stability index, the separation index, concept probability, robustness, predictability, among others. While each of these indices exploit certain variable characteristics in the context, it has been found that the stability index is the most prominent one for assessing the concept quality. So let's take a quick look to the stability index. So given a formal context K, we can obtain the intentional stability for a concept C with extent A and intent B by simply counting the number of subsets in the extent power set that satisfy one of two conditions. So either the derivation of the subset is equal to the intent or the closure of the subset is equal to the extent. So basically, the intentional stability quantifies how the concept intent depends on the object in the extent. So at high level, it indicates how much noise or irrelevancy or overfitting we have inside the concept intent. In a similar way, we can use the extensional stability to quantify how much noise exists in the concept extent. So as I mentioned previously, the stability index actually shows prominence in many applications, but it has two major limitations in general. So the first one is related to its scalability. So it is widely known that computing the exact stability is an NP complete problem. This is actually because to calculate the numerator of the stability, we have to first generate the power set, and then we go through all the subsets in this power set, and we count the number of them that satisfy the derivation condition. So this requires exponential time in the size of the intent or the extent. So in practice, it imposes a computational problems even with medium-sized concepts. The second limitation is related to its accuracy. So if we look carefully to the numerator of the stability, we can see that it's identical to the set of concept generators. And it is widely known that non-minimal generators frequently cause an overestimation of the concept quality. This is because it frequently results in redundant and useless association rules. So taking this as a motivation index to address these two limitations. So intuitively, the approach of our CR index rely or depends on in the following two ideas. So first, we rely on the intent rather than its power set. So In other words, instead of going through all the subsets in the entire power set, we only count the number of the relevant attributes in the intent itself. This substantially improves the computational time by converting it from exponential to linear. The second idea is we leverage the fact that minimal generators frequently results in producing a less redundant association rules and implications, and we use them instead of generators to avoid the overestimation of the concept equality. So now to achieve the first idea, the first thing we do is we define what is a relevant attribute. So given a formal concept C with extent A and intent B, we refer to the attribute M in its intent as conceptually relevant if removing this attribute from the intent violates the intent derivation conditions. So from a conceptual perspective, this means that this condition means that the concept will collapse and doesn't preserve its local conceptual structure if we remove this attribute from its intent. From a statistical perspective, this condition implies that this attribute M has a significant statistical influence on the distribution of the concept intent parameter. On the contrary, if this condition is not satisfied, we will refer to the attribute as not conceptually relevant, since there will be no impact on the conceptual structure of the concept. So for further clarification, let's consider this example, which is a movie formal context with 11 objects representing movies and 7 attributes capturing their categories. So if we take, for instance, this formal concept here in the lattice highlighted in yellow with extent 256 and intent adventure criminal drama, we can see that the attribute drama is conceptually relevant because taking off this attribute from the intent will violate the intent derivation condition, while the two other attributes, adventure and criminal, are not conceptually relevant because removing each one of them has no impact on the extent. So up to this point, we now set the stage for the CR index. So given the formal context K, we can obtain the intentional CR index of the concept by first calculating its intentional alpha and beta terms, and then we apply a function f on their resulting values. To calculate the intentional alpha term of the concept C with a non-empty intent, we first in the numerator go through all the attributes in the intent and we count the number of them that satisfy the conceptual relevance condition. Then we use the intent size as a normalization factor to scale the value of the term between 0 and 1. So intuitively, this term quantifies the amount of relevant attributes in the intent. As an example, the alpha term of our illustrative example is 1/3 because it contains only one conceptual attribute out of 3 in its intent. On the flip side of the coin, to calculate the intentional beta term of the concept, we simply count the number of its minimal generators, and then we use the size of its intent power set minus 2 as a normalization quantity to scale the value of the term. The idea here behind taking minus 2 in the denominator is to exclude the trivial empty set and the intent set itself from the power set. At high level, this term actually quantifies the amount of the relevant local information in the concept that may result in a potential relevant association rules and implications later on. Obviously, also this term can be seen as an improved version of stability. So here the beta term for our example, our illustrative example, is also 1/3 because this concept has 2 minimal generators. The f function in the index serves as an activation function. So it can be thought of any function that can be applied to squash the linear or the non-linear relationships between the alpha and beta terms. So for instance, the arithmetic average that compute the linear additive relationship of the two terms is a simple example of F. So actually the rule of the F in the index is to provide flexibility in adapting the index so that we can obtain the best variant that fits each specific problem. To sum up, by contrasting the CR and the stability indices, we can get the following. So in CR, we depend on the minimal generators rather than generators in stability to precisely evaluate the concept equality. Also in the CR, we consider information about the relevant attributes, which is not taken into account in stability. The formula is CR formula is flexible and can be adjusted from one application to another, while the stability has a unique formula. Finally, the CR has a polynomial time complexity, while the stability has an exponential one. To experimentally evaluate the CR and the stability indices, we first artificial and 4 real-life datasets. So the Dirichlet and coin toss are 2 random formal contexts generated using Dirichlet and the indirect coin toss model generators. The LinkedIn contains information about the interconnected LinkedIn profiles for a set of computer science experts. Diagnosis involve information about a set of symptoms and their medical diagnosis, and media language include the semantic webs for a set of spoken language in different countries. And finally, Dolphin, which describes a community network of 62 dolphins living in New Zealand. Then we applied the following cross-validation schema. So in this schema, we first divide each dataset horizontally into 2 disjoint subcontexts, KR and KT. From these 2 subcontexts, we extract the corresponding 2 sets SR and ST of the shared concept. So the concept in SR and its corresponding one in ST are shared if they have identical intent, but not necessarily the same extent. Now, by using the KR as a training set, we calculate the values of the CR and the stability indices for all shared concept in SR set. And then by using KT as a testing set, we evaluate the resulting values on the corresponding shared concept in ST. After that, for each index, we record the final score list of all shared concept. And by using this list, we calculate 2 validation matrices, which are the Pearson correlation coefficient and the average elapsed time. Consequently, we conduct 2 experiments. The goal of the first experiment is to explore whether the CR index is really accurate more than stability or not. So here, by looking at the Pearson correlation scatter plots, we can see the following. So first, here CR is slightly more accurate than stability on 3 out of 6 datasets, the 2 random ones, Dirichlet and coin toss, and the diagnosed dataset. But in the 3 remaining datasets, so CR is considerably more accurate than stability. So specifically, it was about 16% more accurate in LinkedIn and about 33% more accurate than it in media language, and about 16% more accurate than stability on dolphins. The goal of the second experiment is to validate whether the CR index is computationally faster than stability or not. So here we repeat experiment 1, but instead we record the average elapsed time. So from we can see that CR index appears in blue. Outperforms the stability on all tested datasets. So in particular, it was about 4 times faster than stability on LinkedIn and about 3 times faster than it on media language, and at least 2 times faster than stability on the remaining dataset.